All right, let's talk velocities and rate of change. We've introduced this concept before. The average velocity, well, hold on. Nope, no, hold on. The average velocity is the average rate of change of position. And we had a formula for that we used before. Remember, we said V bar is the average rate of change of position. This is a difference quotient, right? This is the slope of a secant line. It's all connected. Average velocity is the slope of the secant line of the position function. Okay? And this average velocity, which is also a difference quotient, we said as this interval gets really, really close, right, as these two time periods, as the average velocity is over a really tiny amount of time, this kind of looks weird, then it approaches the instantaneous velocity. Well, that's exactly what we've been doing in 3.1, right? Average rate of change, difference quotient, secant line, as that gets really small, that limit is instantaneous rate of change, the instantaneous velocity. This is really just using everything that we've talked about and slamming them together. Okay? So we're going to say that the velocity at some point, and specifically the instantaneous velocity, at some time A is the derivative of the position function at A, which is the limit as t approaches A of this difference quotient, of this average velocity. Okay, tying the concepts together. So instantaneous velocity, that's the new thing here, but it's just the derivative, which is just that limit, like we introduced in the first video. So let's use it and connect it with some more things about limits from the previous chapter. And again, there's a lot of words in these application problems, so I am writing them out beforehand. Feel free to pause and copy them, or you can just reference them in your notes. So we're going to look at example 3. Now we've got a weight that's made out of lead, and it's hanging from a spring, kind of like, here, I'll give you a little picture. There's a little spring here. That's kind of a weird looking spring. And there's a lead weight on the bottom, and it's bouncing up and down, right? Because the weight pulls it down, but then the spring pulls it back up. And it just keeps going doing, 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 etc. And that's the sound it makes. So it's bouncing up and down relative to some horizontal line. So let's call this horizontal line a height of 0. Its vertical position at time t, and we're not given it any units here. I'm gonna make this problem have units. Its vertical position in let's have it bounce a lot. Maybe this is a really big weight. Let's say in meters. At time t seconds. Yeah, I actually don't know if this really works. No, it's not going to be seconds. See, this is why I don't want to include units, because it's going to turn out that it takes like 6 seconds for this thing to bounce down and up. Can you imagine how big the spring would have to be? Or how heavy the weight would have to be? There's a really interesting correlation between how long, like the frequency of oscillation and stuff like this is constant, like based on a couple variables in gravity. Anyway, let's forget the units for now. I don't want to make that up. If I make that up, I'm going to get myself into trouble. So its position, its vertical position is given by a sine equation. So it's periodic, right? It's going to bounce down, bounce up, and then it repeats. Bounce down, bounce up, bounce down, bounce up. It repeats just like sine. It's periodic. Use a table to estimate the velocity at 0 seconds. And again, we're going to assume that 0 is not the start of this experiment, so negative seconds makes sense. We're going to say negative seconds is like what happened in the past. and check your answer using a derivative. Okay. So I took this from the book. I am a little annoyed that they did not give me appropriate units, but I do not want to make them up. So let's approximate this velocity. So remember that v of 0 is going to be the limit of the average rates of change, the limits of the average velocities. As t approaches 0 of s of t minus s of 0 divided by t minus 0. That's the definition of what the instantaneous velocity at 0 seconds means. Okay? Now we're going to estimate this limit with a table. And we've done this a little bit before. Let's look at this. So let's look at different values of t. And let's have these values of t approach 0. So maybe 0.1, 0.01, 0.001. These are very small values of t. They're close to 0, and they're getting close to 0. And then let's look at what does the average velocity look like? The average velocity is given by this formula without the limit. And let's connect average velocity with instantaneous velocity. Because as t is approaching 0, as we go down on this table, these average velocities should also be approaching that instantaneous velocity. So whenever you have to plug in a bunch of numbers, it can be a really good idea. Use Desmos. Okay? So if I pull up Desmos, which is somewhere, let's say s of t is equal to sine of t. Now I want the average rate of change, which is s of t minus s of 0 divided by, we're going to need parentheses, divided by t minus 0, or just divided by t. Now another way that you can use Desmos here is something called using sliders. If you click right here, it's going to tell you, well, all right, I guess that's only for graphs. We're not going to use sliders for this, but we've used sliders for graphs in the past, and it's pretty cool. But anyway, we can now evaluate this by just changing the different values of t. When t is 0.1, this average velocity, the average velocity between 0 seconds and 0.1 seconds is about 0.9983. Right? That's the average velocity in that interval, right? Specifically, this right here is average velocity on the interval from 0 seconds to 0.1 seconds. And as we make this interval smaller, as we calculate the average velocity over tinier and tinier intervals, we're hoping that average velocity approaches the instantaneous velocity. Let's add another 0. Average velocity is 0.99998. I'm in the wrong color. And all right, there's kind of a pattern emerging, and we only have 2 points. Let's add another 0. That was an 8. Not even close, Jason. 0.9999998. All right. What do you think is happening? As t is getting smaller and smaller, and really, if we should also check from the other direction. All right, we should check from the negatives as well. Let's do that real quick. This is negative. Oops. All right, it's doing the same thing from the left. Why is it doing the same thing from the left? It's because this is an odd function divided by an odd function, essentially. Oh, wait, no. Wait, hold on. This is positive, right? This average velocity is still positive, even though we're plugging in a negative. So from the right and from the left, it's approaching 1. So again, we'd say as t goes to 0, the average velocity is approaching 1. So that's our guess for the instantaneous velocity. Instantaneous velocity is just the limit to the average velocities as that interval gets really, really tiny. Let's check our answer using the definition of S prime. Oops, I need another page. So S prime at 0, using the definition that we introduced over here. A is 0 here. S prime of 0 is the limit as t approaches 0 of S of t minus S of 0 divided by t minus 0, and again, S of t is equal to sine t. This is the limit as t goes to 0 of the sine of t minus the sine of 0. T minus 0 is just the same thing as t. Simplify the numerator. This is the limit as t goes to 0 of sine of t. Sine of 0 is equal to 0. Sine is the y-coordinate on a unit circle with 0 degrees. 0 degrees or 0 radians, rather, is this point on the unit circle. What's the y-coordinate here? Y-coordinate at this point is 0. And we get this. And this is not an easy limit to solve. We need L'Hopital's rule, which we talk about at the end of this class, end of this quarter, not this section. But we have this result from earlier. We talked about this result in chapter 2, and we said this is equal to 1. 1 is the instantaneous velocity when t is equal to 0. That was also our guess. That's the relationship. Average velocity, instantaneous velocity. Instantaneous velocity is just the limit of the average velocities. It's just instantaneous rate of change. Instantaneous velocity is just what happens when your averages get really, really close together. And that's why we talked about limits in the first place, because derivatives are these slopes. Derivatives are these instantaneous rates of change. And the only way to talk about that is to talk about them using the idea of two things getting really close together. That's where limits tie in. That's what we got here. And normally your units here would be in like meters per second, miles per hour, feet per second, whatever. This problem didn't give us any units. If you really wanted to do it, you could be like units per other unit. I don't know, but that looks a little weird. So just know that when you have units, we'd want to include them here. All right. In this next problem, which I'm also taking from the textbook, I'm going to do my best to impersonate somebody who knows something about cars. So apparently there's this car called the Hennessy, I don't even know how to say it, Venom GT. I know how to say that part. There's this Venom GT car, apparently, that can go at 270.49 miles an hour. That's pretty fast. Faster than my car has ever gone. Fastest I've taken my car is maybe like 90 miles an hour. In tests, we had a couple things in the test. 0 to 60 in about 3 seconds. That's very fast. 0 to 100 in about 5.8 seconds. 0 to 200 in these seconds. These are pieces of information. Oh, there's one more. These are all pieces of information that tell us the average rate of change of the velocity. Quick note. Quick note. Average rate of change, average velocity, is the average rate of change of position. Average velocity uses information about position. This problem is giving us information about velocities. So we're not going to be talking about average velocities here. We're going to talk about average acceleration. Because acceleration is just the rate of change of velocity. Right? Acceleration is the rate of change of velocity. Velocity, speed, if you will, is just how fast is your position changing. Well, acceleration is how fast is your velocity changing. So that's really what we're talking about here. Rates of change of a rate of change, slope of a slope, derivative of a derivative. Don't worry, that's not going to really come into play just yet, but it'll come into play in the future. So let's actually get to the problem. Use this data to draw a conclusion about the rate of velocity. Again, rate of change of velocity is acceleration as the car is approaching 229 miles an hour. So this is saying, what do we know? Let me rephrase this. What do we know about the rate of change of the velocity at this time? When it's going, we don't know what time that is. We want to know about v prime, which is when it's close to 229 miles an hour. And then there's a second part of the question as well. So let's look at these average rates of change. We can use this information about velocity to find an average acceleration. Just like v bar, the average velocity was using the average rate of change of position. We can get average acceleration the same way. Right, so a bar is going to be v of t minus v of a over t minus a, just like before. So let's make a little table of all this stuff. So we are going to have a bunch of different average accelerations. Right, average acceleration between t equals 0 and some other t. We can call that, I don't know what variable to call it, some other time. I'll leave it blank for now. Is given by the following. So let's look at this first one. It's going from 0 to 60 miles an hour in 3.05 seconds. So after 3.05 seconds, what's our average acceleration? Well, it's going to be the change in velocity over the change in time. Well, what's the change in velocity over here? 60 miles an hour. What's the change in time? 3.05 seconds. That's going to be the average acceleration in this first period of time, which is going to be about 20 miles per hour squared. Miles per hour per hour. All right, so let's look at 60 divided by 3.05. About 1967. That's what the average acceleration is in the first 3 seconds. In the first 5.88 seconds, it goes from 0 to 100. After 5.88 seconds, we have 100 is our change in velocity. Let's type that down as well. 100 over 588. About 17.01. And again, this is in seconds for time and miles per hour squared for acceleration. Let's keep on doing this. Let's do 0 to 200 in 1451. That's a change of 200 in 14.5 seconds. What is that? 14.51, 13.78. And let's do one more piece. In 19.96 seconds, what's the change in velocity? 229.9 miles an hour. What's that average rate of change of the velocity? Of the acceleration, rather. 229.9. And that's divided by 19.96. 11.52. So this is how the average acceleration's behaving. In the first 3 seconds, that's the average acceleration. In the first 6 seconds, that's the average acceleration. First 14 seconds, that's the average acceleration. First 20 seconds, that's the average acceleration. What's happening to the average acceleration? This car is speeding up the whole time. It's going to 200 miles an hour, 220 miles an hour, 230 miles an hour, pretty much, in 20 seconds. This thing is speeding up fast. But what's happening to the acceleration? As time goes on, acceleration's decreasing, right? What did it ask us to do? Draw a conclusion about the rate of change of velocity. The rate of change of velocity, i.e., the acceleration, is slowing down. That's our answer. Acceleration is lessening. Now, the velocity is still positive, right? It's still speeding up. But the speeding up is slowing down. Is a funny way of saying it, but it's 100% true. It's still speeding up, but the rate of speeding up is slowing down. It's still going faster, but it's not increasing its speed by as much. All right, so it's accelerating the whole time, but it's accelerating less as time goes on. Final. Does the rate at which the car is accelerating... Oh, we already answered that. The rate at which the car is accelerating appears to be decreasing. That's our answer to both parts. And that really is kind of pushing the boundaries of this section and getting onto more applications of derivatives when it comes to velocity and acceleration. So it's a little bit of a tease on what's to come, but here are some new concepts. And we'll have another video after this with more application problems as well. Not just velocity, not just acceleration, but other applications of rates of change on top of this. Let me know if you have any questions, and enjoy.